All right, so we should be live right now. Um, so chapter 4 is about work and energy and work energy theorem, conservation of energy, all that stuff. And it also covers the topic of power. So today I am going to talk a bit about power, just for the variety, because I usually at this point would say something about work or kinetic energy. So this time around, we're going to discuss power. And I'm going to use a capital P to represent power. Some other symbols that I will use, capital W will represent work. So this symbol right here, equal sign with a dot over it, I'm going to use to say this thing represents this concept. So that'll be work. E can represent energy, and then T can represent time. So I'm just going to define some terms so that I can use them without having to constantly go back and say them. So we've defined our terms. So now let's do mathematically, what is it that power is telling us? So power is rate at which work is done. So that is basically work per unit time, or alternatively, it is rate change in energy for an object. So energy per unit time, delta E over delta T. This defines power. So 3 bars again means this is defined by this. And this thing is defined by either of these two expressions. Okay. So power is rate of doing work. Power is rate of doing work or changing energy. So power can also be defined as rate at which energy is being changed. All right, so that's what power is. Now let's look at a quick example of power. So I'm going to write the example. Those of you who pop in to watch live, you're going to have to wait while I write all this out. But of course, I'm going to also edit the video later where it'll just show the example written out here. So you don't have to watch through all that. Hence why I always post the edited videos. So the example that I've chosen is, how much power is needed to do 3 joules worth of work in 5 seconds? You'll recall that the unit for work, the SI unit, is joule. The time, of course, is in seconds. The SI unit, for what it's worth in power, is the watt. But let's go ahead and work this problem first. So power is equal to how much work is being done. So that's 3 joules per how much time does it take to do the work. So 3 joules per 5 seconds. So 3 divided by 5 is 0.6. So this has a value of 0.60 watts. And 1 watt is the same as 1 joule of energy or of work per second. So that's how much this unit is. All right, so that is power. That's power in an example. A second example, for what it's worth, might be to turn stuff on its head. So for example, maybe you happen to have an engine. So this engine produces 750 watts of useful power. That's approximately 1 horsepower for what it's worth. But this is the MKS unit, and horsepower is more of a US customary unit. So your engine produces 750 watts of useful power, and we want to know how much time this engine needs to do 6,000 joules worth of work. Now, this of useful power, all that means is just that an engine can produce more power than what is actually used. In fact, there's an efficiency factor associated with any engine. And part of that efficiency factor is you could do how much energy do you put in versus how much do you get out. And so there's an efficiency factor there, but even how much energy do you get out in mechanical energy, not all of that necessarily goes towards actually doing work. So this is how much power is actually going towards doing work. So again, we use our equation that says that power is amount of work done. So delta W over delta T. And so this is the same thing as saying that the amount of time that it's going to take for this engine to do some work is given by delta W, the work done, divided by the power. Notice that I've basically just multiplied both sides by delta T. So that would move the delta T over here. And then I've divided both sides by the power P. And so that puts the power P here in the denominator. So delta T, the amount of time, is the work, that's 6,000 joules, divided by the power, that's 750 joules per second, 750 watts. So look, I can cancel a 0 here and a 0 here. I've got 600 over 75. Note that 600 divided by twice this amount would be 4. So 600 divided by 75 should be 8. So we're looking at something like 8.0 seconds, depending on how many significant figures we need to be retaining. So as always, thanks everybody for watching, and I'll see you in the future. See you next week. And I guess goodbye for now.